Thanks very much. Human-made climate change is a huge moral, political, and legal issue because the people who are causing the problem, and that's us, the older generations, are not the ones who are going to suffer the consequences. Most of the consequences. It's young people, and it's also people in developing countries who haven't done anything to cause the problem. The situation is that there is this huge gap between what is understood about global warming by the relevant scientific community and what's known by the people who need to know, and that's the public. And the truth is, we actually have an emergency, a crisis, but people don't realize it. It's not easy to recognize climate change because it's smaller than the day-to-day weather fluctuations, but it has enormous implications. And the reason this happens is because of the inertia of the climate system. The ocean is 4 kilometers deep. Ice sheets are 2 or 3 kilometers thick. They don't respond quickly as we begin to apply forcings to the system. So that slows down the response. It means that there's more climate change that's in the pipeline, even without any additional changes to the atmospheric composition. We've only realized about half of the warming due to the gases that are already in the atmosphere. And the danger is that the climate system can pass tipping points where the dynamics of the system begins to take over and you have consequences that are out of your control. For example, I'll give a couple of examples of tipping points, but the bad news is that it's become clear in just the last few years that if we want to keep a planet that resembles the one that has existed the last 12,000 years during the Holocene, we're going to need to keep CO2 on the long run no more than 350 parts per million, and we've already got it up to almost 390 parts per million. The good news is it's still possible. By means of reasonable policies over the next several decades, we could get the system, the CO2 to peak and begin to come down and stabilize climate, but we're running out of time. Just to briefly mention a couple of climate tipping points, one of them is the ice sheets. When they begin to disintegrate, if they go too far, it's out of your control. You can't tie a rope around an ice sheet once it begins to disintegrate. The principal process that drives this is as the ocean gets warmer, it melts the ice shelves, which are the tons of ice that come out from the ice sheets into the ocean. And as those buttressing ice shelves disappear, then the ice sheet can discharge ice to the ocean much more rapidly. And we know that this is not a theoretical possibility because we see from the history of the Earth that when ice sheets do disintegrate, once they get started, you get changes very rapidly. As the last ice sheet melted 14,000 years ago, sea level went up 5 meters a century for several centuries. That's 1 meter every 20 years. So you don't want to get to that point. Another nonlinear problem is the effect of climate change on species. We are putting pressure on many species in different ways, but the pressure that's going to be important on the long run is the shifting of the climate zones, which are, a given temperature line is now moving poleward at a rate of about 50 to 60 kilometers per decade. And when that total shift becomes too large, it will cause those species that cannot migrate that fast to go extinct. And because of the interdependencies of species upon each other, that can cause ecosystems to begin to collapse. And again, it's not a theoretical notion because there have been global warmings of 5 or 6 degrees Celsius several times in the Earth's history. They actually were slower than this one. Those warmings took a few thousand years, but warmings that large were enough to drive up to half of the species on the planet to extinction. And then new ones came into being over hundreds of thousands and millions of years. But on any time scale that we can imagine, we would have a much more desolate planet if we drive species to extinction. Now, let me just say one thing about the physics. The physics of this problem is actually extremely simple. When we add carbon dioxide to the atmosphere, we make the atmosphere more opaque in the infrared part of the spectrum. And so the radiation to space, normally the planet emits to space the same amount of energy that it absorbs from the sun. But if you make the atmosphere more opaque, so the radiation emerges from a higher level. Okay, so what I was saying was, as you add CO2 to the atmosphere, it makes it more opaque. Therefore, the radiation to space, the heat radiation to space, it keeps turning on and off, doesn't it? Okay, it's only an inch away from my mouth. The radiation to space will emerge from a higher level where it's colder. Therefore, it reduces the amount of radiation to space, making the planet out of energy balance. And we know we can calculate very accurately the effect of the changes. Now it's on again. We can calculate very accurately the effect of the gases that we've added to the atmosphere within 5%. Everything else fixed, the changes that humans have made to the atmospheric gases will reduce the amount of radiation to space by 3 watts per meter squared compared to pre-industrial times. But we're also doing other things. Especially we're putting particles in the atmosphere, visible air pollution, and that reflects sunlight. Unfortunately, we're not measuring those particles as well as we're measuring the greenhouse gases. So we're not sure. They probably reduce the amount of sunlight absorbed by the planet by something between 1 watt and 2 watts per meter squared. That means that the net climate forcing is something between 1 and 2 watts. Sophie was trying to explain to Connor that it's 2 watts per meter squared, and she had these little 1 watt Christmas tree bulbs. So it's as if we have 2 of those over every square meter of the Earth's surface. But Connor could only count 1 watt, and the truth is, we don't know who's right, Sophie or Connor. It's something in that range. We actually can check this, the physics very well, because where does this excess energy go? Well, the heat capacity of the atmosphere is very small. The conductivity of the land is low, so that the temperature changes only penetrate the upper few tens of meters. And so that's not much heat capacity either. Where the energy has to go is mostly into the ocean. And finally, beginning several years ago with the Argo floats, which are now several thousand of them around the world ocean, which yo-yo down an instrument package to a 2-kilometer depth, and it yo-yos back up, and it measures the temperature of the ocean very precisely. We find that indeed the planet is out of energy balance. The ocean heat content is continuing to increase, and the planet is probably out of balance by about 3/4 of a watt. At any case, by at least half a watt per meter squared. And that means that there's about as much warming still in the pipeline as that which has occurred. If we look at the temperature change of the Earth, during the last 3 decades, while most of the greenhouse gas increase occurred, the temperature has been going up steadily at about 0.2 degrees per decade. And it's going to continue to go up. Next decade it has to go up because the planet is out of energy balance by a substantial amount. So we know that the temperature is going to continue to increase unless we reduce the amount of greenhouse gases in the atmosphere. So let me say just a few words about the different areas which provide our understanding of the system. And I always get hung up on paleoclimate, so I force myself to have this huge amount of information from the Earth's history. But I've included only one chart because I don't have time to get hung up on this. But this shows, the top graph shows the deep ocean temperature over the last 65 million years. And then on the second chart, I've expanded the time scale for the last 5 million years. And then in the bottom chart, I've further expanded the time scale for the last 500,000 years, the last 500,000 years. And so you can see that on the very long time scales, there are very large changes in the climate. In fact, the first, let's see, is there a pointer on this? I guess, yes, there is. So between 65 million years ago and 34 million years ago, the planet was so warm that there was no ice sheets on the planet. It cooled off enough 34 million years ago that ice began to form in Antarctica, and the continent glaciated very quickly. But basically, just to summarize what's happening, I don't have time to discuss it in detail, but on these long time scales, atmospheric carbon dioxide can change a lot. It was more than 1,000 parts per million back at this time. And then what these oscillations are, these are the glacial to interglacial changes. CO2 is involved in these changes also, although it's not the driving mechanism. On the long time scale, CO2 is the principal driving mechanism. The things that can cause climate to change either have to be energy coming into the planet or something within the atmosphere or something at the surface. The amount of energy coming into the planet does change on these long time scales. The sun is a well-behaved main sequence star. It's burning hydrogen to make helium with nuclear fusion in the core, and it's slowly getting brighter over time. So over this time period, it got brighter by 0.4%, which is because the Earth absorbs 240 watts of energy from the sun. That means 1 watt per meter squared increase in the forcing over this time period. But carbon dioxide, and the continents during this time period were already close to their present position. So their changes in the surface reflectivity over this period were small, less than 1 watt per meter squared. But the changes within the atmosphere, we know, were much larger. CO2 changed from 170 parts per million during the ice ages to 1,000 parts per million, is a forcing of more than 10 watts per meter squared. So more than an order of magnitude larger than the competing forcing. So in fact, carbon dioxide is the main main cause of the warming, and it was because the CO2 in the atmosphere is a result of a balance between the source of CO2, which is volcanoes, and the sink of CO2, which is the weathering process. And the source was very large at the time that India was moving through the Indian Ocean, but when it crashed into Asia and began to push up the Himalaya mountains and the Tibetan Plateau, then that source, which the volcanoes are associated with the continent subducting ocean floor beneath it. And so once India crashed into Asia, then that source diminished and the weathering sink increased because of the Himalaya mountains going up. So the planet has cooled off over this time period. And then these oscillations are driven by perturbations of the Earth's orbit, which affect the distribution of sunlight on the planet. In particular, when you get more sunlight on the poles, it tends to melt the ice sheets. And as the ice sheets get smaller, that makes the planet warmer because it exposes darker surface. And that, as the planet gets warmer, the ocean gives up CO2. And the CO2 is an amplifying feedback. So in these oscillations, the CO2 is just an amplifying feedback, but it causes half of the amplitude is due to the CO2 amplifying the change. But the main point I want to say from paleoclimate is that natural process, the imbalance of the source and sink of CO2 is of the order of 1/10,000th of a ppm per year. Humans are now increasing CO2 2 ppm per year. So we're 10,000 times more powerful than the natural geologic changes in the atmospheric composition. And also, we could estimate from those climate changes that there was only 450 or 500 ppm at the time Antarctica froze over, and this is a reversible process. So if we burn all the fossil fuels and increase CO2 to 800 to 1,000 ppm, we're going to melt all the ice on the planet, and sea level will go up 75 meters, 250 feet. We can't say exactly how long it takes, but when ice sheets do begin to disintegrate, the process becomes very fast. Now, to turn to observations of current, what's happening in response to the rapid increases in greenhouse gases in the last few decades, we see that the sea ice, the Arctic sea ice, the amount we began to measure from satellites in the late 1970s, and the amount there fluctuates each summer depending upon the weather that summer, but overall it's decreasing quite rapidly. And this year's summer sea ice, the Northwest Passage was open again for the second time in the last few years, and those were the first times in recorded history. We're going to lose all of this Arctic sea ice. If we continue on business as usual, within the next few decades, we will lose all of this Arctic sea ice in the summer. There are also effects on Greenland, which the red part is the area where the summer melt. And again, we have accurate measurements from satellites beginning in the late 1970s. The area with melting fluctuates from summer to summer, but it's increasing. And that meltwater will go to a low spot on the ice sheet, burrow a hole in the ice sheet, go to the base of the ice sheet where it lubricates the ice sheet, and it speeds up the discharge of these giant icebergs to the ocean. And we can now measure very precisely the mass of the ice sheets using the gravity satellite, which has been up there for only 6 or 7 years. But we see that during the winter, the ice sheet gets heavier, and then during the melting season, it loses mass. But overall, it's now losing mass at a rate of more than 200 cubic kilometers per year. And Antarctica is also losing mass. And what's a little scary about this is the fact that the rate at which it's losing mass seems to be increasing. And that's the tipping point that we don't want to see happen. If this, right now, sea level's only going up 3 centimeters per decade, which is not negligible. It's more than a foot per century. But the danger is that this is going to fall off the edge, and we'll get meter scale sea level on time scales of decades. Another effect that is expected of global warming is an expansion of the circulation cell, the rising motion in the tropics and the subsidence in the subtropics, which causes the subtropics to be dry. That circulation cell is expected to expand as the planet gets warmer. And we observe empirically that it has expanded by about 4 degrees of latitude on the averaged overall longitudes. And that's one of the reasons that Lake Mead and Lake Powell are only half full. It's also one of the reasons that forest fires in western U.S. have been increasing, and also in the Mediterranean region and in Australia, which are also bordering on the subtropics. And these fires now burn hotter, and it's much more difficult for forests to recover as these fires burn hotter, because it burns the seeds as well as the trees. Glaciers are receding all over the planet, in the Rocky Mountains, the Andes Mountains, the Himalayas, the Alps. Glaciers are receding, and this is very important in some regions because some of the major rivers of the world have more than 50% of the water during the dry season coming from the melting glaciers. So once the glaciers are gone, then you'll have bigger floods in the spring, but the rivers will tend to run dry in the dry season. Another effect is on coral reefs, which are under stress for several reasons, but two of the most important ones are the warming of the ocean water, which causes the coral to expel their symbiotic algae and die, and the acidification of the ocean. As we increase the amount of CO2 in the atmosphere, the ocean becomes more acid, and those animals that have a carbonate shell or carbonate skeleton are harmed. In fact, they can't live as their shells begin to dissolve. It becomes too acid. So for all of these reasons, we argue that if we want to keep a planet that resembles the one that has existed the last 12,000 years, the time that civilization developed, we should decrease CO2 to no more than 350 parts per million. The most quantitative way to estimate this is the one I mentioned earlier. We know how far the planet is out of energy balance. If we want the Arctic sea ice to stop melting, then we've got to restore the planet's energy balance. And that means reduce CO2 by at least 35 to 40 ppm. So it's very clear that if we want to preserve a planet like the one we know, we need to do that. And that means that we can't burn all of the fossil fuels. The purple parts are what we have burned already and put into the atmosphere. If we would phase out coal emissions over the next 20 years and leave the unconventional fossil fuels like tar sands in the ground, then CO2 would peak at something like maybe 425 ppm, and it would slowly decrease. It would take centuries to get back to 350, but by means of replanting the forests on marginal lands, there are some ways we could get it to come down more quickly. But the fundamental point is that we would have to phase out the coal emissions rapidly, and we'd have to leave the unconventional fossil fuels in the ground. But what's actually happening? The United States has recently signed an agreement with Canada for a pipeline to carry tar sands oil to Texas oil refineries. And coal-fired power plants are being built all around the world. So there's a huge gap between the rhetoric and the reality. The politicians say the right words. They say we have a planet in peril, and yet their actions are really greenwash because they're very small perturbations to business as usual. In fact, if we look at what happened since the Kyoto Protocol went into effect, emissions were going up 1.5% per year prior to that, and since then, despite this recession of the last 2 years, the emissions have grown 2.5% per year. And governments are just going right ahead. You may have seen the article in the New York Times a few days ago. It had words this large that said, fuel will be found, or something to that effect. They're just assuming we can burn all the fossil fuels, and this guarantees disaster for young people if we do that. So the fundamental problem is this, and it took me a long time to realize this, even though it's so simple. It's as certain as the law of gravity. As long as fossil fuels are the cheapest energy, people are going to keep using them. Of course, why are they cheapest? Partly because they're subsidized, but mainly because they don't have to pay their cost to society. The human health effect of air and water pollution from fossil fuels is enormous. 1 million people a year die from air and water pollution, but much more than that, people's health are affected, and those medical bills are borne entirely by the public. Fossil fuel companies don't have to pay for that, nor do they have to pay for the damage to the environment or to the future of young people. Those costs are external. So, what we should do is clear enough. We have to make the fossil fuels pay for their true costs. That means apply a fee, but it has to be very simple. Should be across the board at the first sale, at the domestic mine or the port of entry. And all of the money, I think, has to be returned to the public. You do not want Congress trying to decide where they're going to invest this money, which special interest they're going to give it to, or for them to try to pick winning technologies. Of course, the government needs to provide some support for technology development, but not from this money. This money should go 100% to the public, and that way the marketplace will make the decisions as to what the winning technologies are. And that's a point which Republicans, by the way, and conservatives can appreciate. There's even an organization, I think it's Republicans for the Environment or for Conservation, which has read about this fee and dividend, and they say that's exactly what is the appropriate approach. Let the market make the decision. It does not require any increase in the size of government. All they have to do is divide by long division, divide by the number of legal residents and send them the money. And that way you keep the big banks out of it. There's absolutely nothing added by the big banks. They don't need to be involved in this. And it's the only way that you can get a global agreement. How can you possibly, there's no way that China or India is going to accept a cap. And why should they? Their emissions per capita are much smaller, and their contribution to the climate problem is much, much smaller, because it's the integrated emissions over time, the cumulative emissions, that cause the climate change. And we're 10 times more responsible than China, even though China's emissions now exceed ours. We're 10 times more responsible per capita for the climate change. So the merit of this approach is that it would stimulate the economy and put money in the public hands. And that's the only way that we're going to solve our fossil fuel addiction. And I think it's the only way that's feasible on an international basis. I'd like to draw attention to the intergenerational injustice of what we're doing and what our governments are continuing to do and to do nothing about. And that is the fact that, as I said at the beginning, the people who cause the problems are not the ones who suffer the consequences. I mean, if the public understood this, parents have always been willing to sacrifice for their children, let alone doing the opposite, where they're causing enormous problems for them. And this is true of all cultures. But the problem is that the governments think that they can set the emissions at whatever level they choose. So I think, I wanted, I put in to remind me, I wanted to acknowledge the many young people who are at this conference today, and I think the only way we're going to solve this problem is if young people begin to get involved and put pressure on the government to do what is needed. And some of us, although we're amateurs, are trying to do some things to draw attention to this. So you may have heard about this Million Letter March. Well, that is why this day we wanted to take some photos of Sophie's my first grandchild. And so she was writing a letter to President Obama. And she did this on the spot. And she wrote some very sensible things. She said, "Why don't you listen to my grandfather?" that morning, her younger brother, Connor, and I had been trying to burn a piece of coal. I wanted to show them how dirty coal is. So she also had that in her letter. And so I was reading her letter, and she was looking at me to see if I was approving her letter. She seemed pretty confident that I was going to approve it. And then we were celebrating her good letter. But I also, now my son, my son has 2 children, so now we have 4 grandchildren. And Jake he's just 2.5 years old, but he's a giant for his age. He's a gentle giant. He's in the upper 1% for his size, so the charts say he's going to be 2 meters tall. And he thinks he can protect his baby sister. His baby sister is just 2.5 days old in this photo. But the truth is, if we don't get on a different path, that it doesn't matter how strong these young people are, they're not going to be able to fix the problem if the dynamics begins to take over. And so one thing that I think we also have to consider, by the way, so there are 2 reasons that I have some optimism that we can make progress on this. One, I came back from China. China is making enormous investments in clean energy. They're now #1 in production of solar and installation of solar energy, wind energy, and they're building 24 nuclear power plants. And I think, I wrote an op-ed the day before I went there, for the major South China newspaper, saying first of all that the world needed Chinese leadership because it's not getting it elsewhere, and trying to argue for a carbon price in China. And I think that there's a very good chance that they will adopt an internal carbon price because they want to phase out the dirty energy. Because they'll suffer more from climate change than anybody. They also have very dirty air, which they need to clean up. And by doing this, they will be out in front in these technologies and be able to sell them to the rest of the world. And so I think that's it. And you know, I realized that what I've been saying for the last year or 2 is actually not right. I had been saying that to solve this problem, we've got to get an agreement between China and the United States to have a carbon price and negotiate some mutual rate for that. But first of all, that's never going to happen. You would have to be approved by the Congress, and Congress is not going to do that. But I don't think it requires the United States. I think if China starts with a small carbon price themselves, then it requires some other countries, some European countries, to agree to that, and then to decide to have, and if they did that, they can put a border duty on products that are made with fossil fuels from any country that doesn't have a carbon price. I think that will cause those countries that don't have a carbon price to have a very strong incentive to have an internal carbon price. And it may be that the initial agreement doesn't include the United States. But it's essential that we get a global carbon price, or otherwise we're going to keep burning fossil fuels. And we can't do that without the other source of optimism that I have is the fact that I think we can sue the government to do its job. The first line of the Declaration of Independence says we hold these truths to be self-evident that all people are created equal. And that led in the Constitution to the concept of equal protection of the laws. And it was the equal protection amendment that was the basis for civil rights, for the courts ordering the government to give minorities equal rights. For example, ordering school desegregation. And they could ask the government to come back and give them their plan for how they're going to desegregate. Well, the government should have to give a plan for how it's going to reduce its emissions at a rate that gives young people the chance of having benefits of nature that we have. And so I think that's, I think that needs to be pursued. And I think I should stop at this point. Okay, my time. Thanks.